Hello students, good morning.
Good morning, ma'am.
Good morning. This is section C, right? Hello students, very good morning to you all. Can you hear me?
Yes, ma'am.
Rajasri, right. I think some of you are responding but without unmuting. That's why I'm not able to hear your voice. Okay. Thank you 4C3, Rajasri, for your response. Right, let us move. All others I do not know. I think they are not in a position to unmute themselves. That's why they are silently listening. Some people are saying why they are not able to unmute all that they are saying. Okay. Let us discuss about the filters. We are discussing about various active filters. Okay. What is an active filter? The active filter uses the active components like OpAmp and the passive components like resistors and capacitors. So active filters are designed with OpAmp and resistor and capacitive elements. Okay, then here we have seen about low pass filter, first order low pass filter, and second order low pass filter. So we have seen the classification of filters, right? And some practical filters also we have mentioned. I have mentioned. Okay. And in today's class, we are going to study about first order high pass Butterworth filter. Okay. So let us see. I told you already that why we are taking Butterworth response. Okay. First thing is it is easy to design, and then its properties are flat pass band and a flat stop band. This is the practical filter that we are considering in our discussions, right? That means we are designing only Butterworth filters. Okay. Then what are the filters that we are designing based on frequency? Maybe a low pass filter or high pass filter, band pass or band stop filters. Otherwise, we say that it may be any order, low pass, high pass, band stop, any order filter. That means we can design first order filter, second order filter, then third order, fourth order, any higher order you can design. So why we go for the order of the filter? That means various filters why we are designing means we came to know that when we were discussing about the second order low pass filter, I have mentioned, right? First order low pass filter frequency response curve we have drawn, and that curve in a stop band, this frequency response, that means gain magnitude curve, gain magnitude is decreasing at 20 dB per decade rate. Okay, so roll off is 20 dB per decade. That decrease we call it as roll off. Now, if you want to have that roll off at a faster rate, then we have to increase the order of the filter. That means if you go to second order filter, then this roll off is 40 dB per decade. So if you want to have higher roll off, that means soon it should come down to 0. That means the stop band gain should be should reach smaller value at a faster rate. So in order to have high roll off, we go for higher order filters, right? So before we discuss about this high pass Butterworth filter, I know yesterday we have not discussed about these filters. Therefore, some of you might have forgotten. And not only that, when you recollect, when you see the previously learned information, then you will be able to recollect very easily, and then we can move forward. So therefore, let me once discuss, let me once show what are the various things that we have discussed. From low pass filter I want to come, because this high pass filter is designed with just slight modifications of low pass filter only. Therefore, and high pass filter is designed with what is that? With interchange of R and C components in low pass filter. So I told you at the beginning of the classes also, right? A low pass filter is the basis for all the filters. Therefore, first class I have discussed about only low pass filter with more attention. Second class I have revised about first order low pass filter, and we have studied about the second order low pass filter. Now this is the third class. Again I want to stress on first order low pass Butterworth filter. Then only we move forward to the first order high pass filter. So why this low pass filter is the basis for all filters, right? So therefore, sometimes in the examinations they ask only low pass filter. Sometimes they ask any other higher order filter. Sometimes maybe band pass filter or band elimination filter, whatever they want, they ask, right? So whatever question we get in the examination, we are not supposed to leave that question because we know already about low pass filter. So a slight modification of it only the next filter. That means if you learn low pass filter properly, then if you get in the examination high pass filter, what we have to do? Exchange this R and C. That's all. You have learned high pass filter. Then you go to band pass filter. So what is this band pass filter? It is one combination of high pass filter and low pass filter. So you know, just now you have learned what is high pass filter, and then you know already the basic low pass filter. You combine these two, output of high pass filter you give to low pass filter, you will get band pass filter. Over. So that means if you learn this low pass filter, you have command on all other filters, right? Again, similarly, a band elimination filter or band reject filter. So how do you design band reject filter? It is like what is that? A combination of low pass and high pass filters. So you know already low pass filter, and you join high pass filter. That's all. It is band elimination filter, right? So therefore, if you learn this low pass filter, you can design any other filter. That's why every day I am showing this low pass filter to you. So what is there in this low pass filter? This is also very simple. What is this? Here we have what is that? OpAmp 741 or 351, right? Then plus VCC and minus VEE. Then this OpAmp is connected in non-inverting mode, right? So you know that this filter is designed with RC components, right? So at the non-inverting input terminal, you are giving R and C. So only thing that you have to remember is if it is a low pass filter, R is connected to the from the source, R is connected. After that, capacitor is connected, right? If you remember only this, that is sufficient, right? If it is high pass filter, you will be exchanging this R and C. If it is band pass, combination. If it is band elimination, combination. So therefore, in this low pass filter design also, I think you can close your eyes and design this low pass filter, right? So OpAmp, and at the non-inverting input terminals, R and C, of course, the input voltage, and at the inverting input terminal, the feedback resistor and the input resistor, the resistor that contributes to gain of the filter will be connected. Just R1 and RF are connected here. That's all. And of course, load value, load resistance, just name it as RL, RF, R1, RC input. So that means now itself, if I ask you to design or draw the circuit diagram of low pass filter, you can draw, and without showing high pass filter, if I ask you to draw high pass filter circuit, we are going to draw just by exchanging the components R and C. Am I correct or not? Right? So I think you are responding positively. Now let us see this low pass Butterworth filter. Here one day when I was explaining, I have skipped one step and I asked you to do it at home. So I guarantee that none of you have done. So that's why once again I want to show that. So otherwise, forever after your BTech, you will get job and you will retire from your job. But forever, your notebook will be there with the gap, right? That means in your notebook, gap will be there forever because you never look at the book after the class. I know that as students. So that's why to be on safe side, let me help you. So that means if I spend time, you are spending time. If I don't spend time on anything, you won't spend. That is natural. So therefore, let me once show you this. Okay. Here for this low pass filter analysis, what we are doing? We are trying to express what is V naught. V naught is equal to, because OpAmp is connected in non-inverting mode, V naught is equal to 1 plus RF by R1 into V in, right? So V naught is equal to 1 plus RF by R1 into V in. So what is V in? V in is equal to this input voltage at exactly at the non-inverting input terminal of the OpAmp. So it is V1. So what is this V1? That is what we are trying to express, and we'll substitute that V1 here. That means V naught equal to 1 plus RF by R1 into V1. That V1, what is this V1? So that V1 we estimate or we express by applying voltage divider rule at this point. Okay. So because we want to know what is voltage V1 here. So for that, what we want to do? We want to apply voltage divider rule. Voltage divider rule. So I have explained many times this voltage divider rule. So that is voltage drop across a particular element is equal to that element impedance divided by total impedance into input impedance. If I want this voltage, how do you write? R divided by R minus JXC into V in, right? If I want this voltage, we write minus JXC, it's impedance or capacitor reactance, right? Divided this impedance. For example, if there is one more resistor, we have to write that R minus JXC, right? So minus JXC divided by R minus JXC into V in. JXC minus JXC, this impedance divided by R plus this impedance into V in. So this voltage divider rule, so many times we have been using, right? I think by now all of you might have learned what is this voltage divider rule. That too, in second year itself we have studied, but whether you remember or not, from the beginning, right, from unit 2 onwards, so many times we have used this voltage divider rule, and almost all the times I have explained this rule, right? So by now you got this. So by using this voltage divider rule, just now what I have mentioned, V1 is equal to minus JXC by R minus JXC into V in, right? After that, what I have mentioned, you just substitute wherever we have minus JXC, you replace it with 1 by J2 pi FC. That means XC is equal to 1 by 2 pi FC. We have substituted. That's all. Okay. So now after that, when we rearrange that equation, I said that we will get. Okay. After rearranging this equation, I said that we will get this expression, right? So this is what V1 is equal to V in divided by 1 plus J2 by FC. So I think some of you have done this rearrangement, right, from here, and some of you, I don't know, some of you might not have done this, right? So anyone who have done this, please share in chat box, take photo of it and share in chat box. Otherwise, I told you, no, forever it will be like this gap will be from this equation to that equation, forever gap will be there, right? Any one of you have done that? If you have done, I'm sure that you will get excellent job in future. So no response, I know, right? That for ordinary questions also you people are not giving response, right? You please try to interact, okay, whenever you get an opportunity. Section C students especially, right? So you also should respond. Then only, okay, my happiness, all that is different whether you respond or not. I will ask question, I will give answer, I will complete my classwork. That is different. But unless you train yourself to respond, what will happen means throughout your life you remain silent like that, and you will be the loser in future for your silence, right? So of course, what is that? To speak is silver, silence is gold. Not all the time. When the teacher asks question, ma'am, if we are silent, we are like gold. No, right? Whenever you get an opportunity, if you go for your interviews and all, if you remain silent like this, because you are training yourself, whenever there is question, maintain silence. Then because you are training yourself like this, when you go for your job interviews, you will not respond. You have trained your mind like that. Therefore, because we are your teachers and we are training you, we have some patience and we try to help you. Therefore, we will wait for some time. Yamma, one of you respond, we say. But the person who is going to give you a job, they just eliminate you within 1 second. That's all. They need not ask you again and again. See, one of you respond. See, I'm going to give you a job. All that they won't say, right? So you please, section C people, many times I told you that you are interacting less, right? So you just unmute your mic and interact. So if you interact, you are training your mind to respond, and you will have the same habit. And finally, wherever you will be special in your class, right? Okay, in your group, in your peer group, right? So now, no problem whether you respond or not. I teach my class. I complete my syllabus. I will explain everything. A question, whatever question I ask, I will answer. No problem. But you will remain as a loser if you maintain the same silence. Okay. So please, all of you, please try to respond. At least some of you. In general, there will be at least one student to respond. But I don't know. Our class, none of you are responding, right? So maybe there are some other students teasing the other people who are responding. Beginning, actually, I observed section C, people are very active, very interactive, all that. Okay, because of your silence, you are losing something. I will tell you later what is that you have lost. After 2-3 days, I will tell you, right? One thing you lost, I will tell you that. Okay, so now any of you have completed? See, you are the students, you have your own characteristics. If I am also as a student like you, I will maintain the same, more or less same characteristics. Of course, there will be some slight variation from person to person. Okay, so whether you do it or not, no problem. You are in learning stage, but your response is important. So one of you tell me whether you have rearranged that equation or not. Yes or no? At least in chat. There are 51 students. None of you are responding. Okay. Right. Right. We are studying communication now. Communication subjects. This is the transmitter, and this is the receiver. Right. So sometimes you are transmitting and I am receiving, and sometimes I am transmitting and you are receiving. Okay. So the distance between the transmitter and receiver remains same. Right. You remember that. Maybe this may be transmitter sometimes, and this may be receiver. And this is the transmitter and this is the receiver. So distance between transmitter and receiver remains same. Okay. So therefore, what do you say in our Telugu? We have some proverbs, right? According to your response only. If you show interest and if you respond, I'll give you more and more information. If you do not respond, I just will have superficial what is that relationship only, right? So here I think From your silence, I understand that none of you have done this. So this I want to show, right? That is V1 is equal to minus JXC by R minus JXC into V in. And now if you substitute wherever we have, so here what I do is in this equation, you divide numerator and denominator with minus JXC, right? In this equation, you divide numerator and denominator with minus JXC and tell me what is that you get. Okay, so then what we get, it is equal to minus JXC divided by minus JXC, so it is 1. That means this V in we can write, right? Otherwise, let me also write like this. V in as it is, let us write. Okay, so numerator minus JXC is there already. Minus JXC is there already, divided by, now numerator we are dividing with minus JXC. So minus JXC, and denominator also we are going to divide with minus JXC. That means in the denominator what we have, R minus JXC, R minus JXC divided by what we said, you write with divide with minus JXC. So minus JXC, minus JXC. So now after writing this, what will be, what is that? This is V. Okay, actually this I thought of writing. Okay, V in is equal to, right? V1 is equal to, V1 is equal to, V1 is equal to this V in, right? This V in into minus JXC divided by minus JXC, R minus JXC divided by minus JXC. Right, now what you will get, minus JXC gets cancelled. I think, and here R by minus JXC you will get R by minus JXC. Here minus JXC by minus JXC 1. So plus 1 you will get. So finally we can write V1 is equal to, V1 is equal to, right? V in numerator 1 only, no? So therefore V in divided by R minus JXC minus JXC, R by minus JXC, this one, R by minus JXC plus 1, plus 1, right? Now we know that we have written here minus JXC is equal to 1 by 2 pi FC, 1 by 2 pi FC. So therefore here you have minus JXC, in this place you write 1 by 2 pi FC. That means this term goes up and you will get here, V in divided by V in divided by this 1 plus you can write, okay, first let us write this only. So minus JXC place we have J2 pi FC, and numerator we have R. Therefore all that we will get here, R multiplied with, so 1 by minus JXC, it is equal to J2 pi FC. So J2 pi FC, J2 pi FC, and this plus 1 as it is you write, plus 1 as it is you write. So that means V1 is equal to V in divided by 1 plus J2 pi FCR. That is what I have written in the next equation. This is what V1 is equal to V in divided by 1 plus J2 pi FRC. So in the previous class, I asked you to do this part, right? So it is almost like very simplest part, but why I have given this again means some of you pay some attention, some of you do not pay attention. So therefore, I want to write once. Okay. Some people, because the same procedure we are going to do for high pass filter also. Okay. Same procedure for high pass filter. I think you can do on your own, right? Just I am giving you in detailed manner for low pass filter. So is it clear to you? Again, silence idea. Right? Is it clear to you or not?
Yes, ma'am. Clear, ma'am.
Again, silence. Thank God someone responded. 406. Okay, okay. So I think now you respond, now one of you. 406.
Yes, ma'am. Clear, ma'am.
Yes, yes. Okay, 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 good. So I'm sorry. I think I have my speaker did not work in my phone. That's why I'm not. That means I have not included my speaker. I think so. Now I am able to hear. Right. So it is clear to you, right? And like that, after expressing this V1, V0 is equal to 1 plus Rf by R1 into V1. And finally, V0 is equal to this and this one. Remaining things we have studied and we have recollected. So I need not spend much time. Only those two steps which I asked you to do on your own, I know for sure you will never do. So why should I leave it like that? Madam asked us to do on our own, you may feel. So I want to show that also be not. And the operation of the filter we have explained, that is at f equal to fh, at f less than fh, at f greater than fh. In our what is that revision time, I have mentioned everything and we have designed filter. So this also I want to mention once, because what are the filter design steps for low pass filter? They are same for high pass filter. They are same for high pass filter. Therefore, all of you please follow once again the filter design. Choose the value of high cutoff frequency first, then select value of C, which is less than or equal to 1 microfarad, then calculate the value of R using FH equation. Then by using this, what is that, AF, that is pass band gain of the filter, 1 plus RF by R1, you select values of, select the value of R1 and calculate what is RF. Okay, so that is what about filter design procedure. So then we have taken the problem and we have applied that knowledge in designing this problem. So we have done this problem clearly and we have recollected also. So this is the circuit we got. So for the same circuit we are going to, that means similar to this we are going to design high pass filter, right? And frequency scaling. What is this frequency scaling? So the same concept what we are learning for low pass filter is same for high pass filter. Therefore, let me also restate what is frequency scaling. So you have designed your filter to have some frequency, some high cutoff frequency, and after that you want to modify the high cutoff frequency of your filter, and therefore the procedure to change original cutoff frequency to a new cutoff frequency is called frequency scaling, right? The procedure to change original cutoff frequency to a new cutoff frequency is called frequency scaling. So how we do that? Just we take the ratio of original cutoff frequency and new cutoff frequency and we multiply it with R in general. So you can also multiply it with C, but we generally select the value of C and we use variable resistor or potentiometer in place of R. Therefore, in general, we multiply that ratio with R and we replace R value accordingly, right? So, based on this concept, that means using frequency scaling technique, we are asked to convert 1 kilohertz high cutoff frequency to 1.6 kilohertz high cutoff frequency. So that also we have done. And of course, here for convenience sake, I'm showing, but without showing this slide, we have designed on our own. Okay. Then after that, plot the frequency response of the low pass filter designed in problem. So yeah, I mean, next class I asked you to share here But section A, at least a few of them have shared. Section C, last class you have not shared this frequency response. At least in this class, I'm expecting you to share. Otherwise, I understand that you people are not that much interested in your studies. So I don't give additional information. Just I give whatever is required. I don't do anything extra if you are not interested. Okay. So generally, if we have a structure, if we have basic structure, we can extend it. So if I concentrate more on extension without having basic structure, it is useless. Therefore, if you are interested, I'll give more additional information so that you can do your competitive exams like a GATE or engineering services, such exams very easily. When I give this additional information, I'm thinking and I'm giving. So if you have no interest on that, if you want to become some other engineer, so for you it is waste of time. So I stop giving that. Okay, it is up to you. According to your response, I add or I delete the information that I am giving. Okay. Now, for LKG students, if I talk about second table, it is useless for them, right? Similarly, for you, if it is useful, I will discuss these additional points. Otherwise, I just keep quiet. Okay. So now, this frequency response plot, how to draw this frequency response plot also I have mentioned, but I asked you to do this at home, right? So, and also I have mentioned what are the frequencies that you have to select and how to calculate these gains even in the previous class, right? And if you draw, you will get this type of frequency response. Now, I'm expecting at least one of you to share that in the chat box. Let me check your chat box for the frequency response. So someone said, yes, Madam Prasanna. Okay, I think for my previous question, I think. Okay, now one of you take photograph of the response problem that you have done in your notebook and share it in the chat box, right? Otherwise, if you feel difficult, of course, nowadays you people are sharing many other subjects also I have seen. So if you feel difficult to share, at least in words you respond here. Yes, ma'am, I have completed that problem or something. I will understand and I believe you, right? So any response is expected from the students now, right? So if you remain silent, it doesn't look nice. So one of you should respond. At least some of you. Okay, then if no one responds, once again I give you opportunity. Right, someone said completed, ma'am. Okay, ma'am. Who is that? Okay, Prasanna said completed this problem. Only Prasanna or any other student? Yes, Pravalika. Very good, very good. Right? Very good, very good. Soumya. But one of you, any one of you, please share so that all your friends will understand that okay. Otherwise, what they think now? See, these people simply they are saying yes, Tanuja, very good. Simply they are saying they are cheating, madam, like that. Your friends will feel. Any one of you, no problem. Whoever it is, but you take snapshot of your notebook, snapshot, and share here in chat box. Only one, any one student. After getting one response, very good, ma, Narendra, right? Narendra also completed this. Very good. All of you are listening to me. From this, I understand. But only one, at least one figure I am expecting from you. At least one student figure. So you are hesitating because of your writing or your notes is not good. All that. No problem. We all are classmates. Your classmates only will see, no other person. If at all, if any other persons are there, means they are our well-wishers only. Therefore, you need not worry. Just share this. Actually, my today's plan is to complete high-pass filter. But high-pass filter, unless you are not perfect, unless you are perfect in low-pass filter, you cannot understand high-pass filter. That's why, again, I am taking 1 more hour for low-pass filter now. Right? Half of the time is over, 9:34. Okay, nobody is sharing. So this type of frequency response we will get for all your friends they have done. All others also you please complete it, right? Please complete and do. So always it is good to follow the instructions given by your professors or lecturers. Okay. Then a second order low pass Butterworth filter we have seen. So when we say second order, we have added one more. When we say second order filter, we add one more RC network. We add one more RC. Oh, wonderful, wonderful, right? So some of your friends have shared. Very nice, ma. Very nice, very nice. Right, Soumya. Excellent. You have done very well. So I'm extremely happy that I have such good students in my class. Right, frequency response and also the problem. Very good, ma'am. Thank you so much. Right. So if we have response like this from you, we will be encouraged. We are also human beings, right? If there is no response, we understand that, okay, why should I struggle this much? We will be discouraged. Natural it is. Okay. So of course, we means the teachers, right? But people like us, somehow we try and try our best to get response from you. We never get discouraged. Right. Very good, ma. Thank you. Let us proceed. Now, second order low pass Butterworth filter. Second order low pass Butterworth filter. So one RC network. That means if it is first order, one RC network. And second order means we add one more RC network. That's all. So what all we have studied now is same, right? What all we have studied now is same. So for this type of filter, how will be the frequency response means the gain magnitude gain decreases with 40 dB per decade, right? So this decrease is like minus 40. So because I'm using the term decreasing, I'm not using this minus always, right? So decrease or it is roll off is at minus 40 dB per decade. So for this type of higher order filter, I mean second order filter, high cutoff frequency is equal to 1 by 2 pi RC. That means you just observe. Here also I have given you the hint, right? What is that hint? For low pass, first order filter, FH is equal to 1 by 2 pi RC. 1 by 2 pi RC. Now here, if R2 equal to R3 is equal to R, you will get R square here, right? R square here. And similarly, C2 equal to C3 equal to C, you will get, in place of C2, C3, you will get C square. So this square and square root cancelled and you will get RC only. So it is 1 by 2 pi RC. That means FH is equal to 1 by 2 pi RC. Otherwise, if the values of, that means for higher order filter also, FH is equal to 1 by 2 pi RC only. When R2 equal to R3 equal to R and when C2 equal to C3 is equal to C. If they are different, then we have to write R2C2, R3C3. So that product you have to write because they are different and compensation. So we'll get under root also, right? So like that, if you know the low pass filter, whether it is, I mean, if you know first order low pass filter, you can design second order low pass filter. You can extend your knowledge to design second order low pass filter. And the gain magnitude is same. So because FH is also same, therefore gain magnitude is also same. But here, if we will get whole power 4, right? 2 RC components. Therefore, we will get whole power 4. That is the only difference, right? Then AF is equal to pass band gain and pass band gain is AF is equal to 1 plus RF by R1. F is the frequency of the input signal. FH is the 1 by 2 pi square root of R2, R3, C2, C3, which is nothing but a high cutoff frequency, right? And again, filter design procedure also same, right? See, not only this filter, all the filters design process is same, right? Only for second order filter, we have to, what is that? To guarantee this Butterworth response, we have to adjust this gain to 1.586. This is the, what is that? This is proved by scientists. Therefore, we have to, in order to get Butterworth response, we have to set the gain to 1.586. Therefore, AF is equal to 1 plus RF by R1 is equal to 1.586. So then we will get AF is equal to 1 plus RF by R1 equal to 1.586. So RF by R1 is equal to 1.586 minus 1, it is 0.586. So RF is equal to 0.586 into R1. So only this is the new point that you have to remember for second order filter. All other filter design steps are same. That is, select high cutoff frequency, select the value of capacitor, and here, as I have mentioned, because there are two RC networks, always you try to make R2C2, R2 R3 equal to R, C2 C3 equal to C. You choose any value less than 1 microfarads per capacitors. Okay, and using that FH equation, you calculate R. That's all, right? So then, based on this knowledge, we have done one problem, that is second order low pass filter. Design a second order low pass filter at high cutoff frequency of 1 kilohertz. So for this, we have done this problem in a very clear cut manner, right? And again, draw the frequency response for filter design. That means just now your friend showed, no? So the same plot, same type of plot you have to do for this circuit. For this circuit also, for this filter also, I asked you to draw this frequency response plot. I think your friend showed a response plot for this, I think. For this circuit only you have shown. This is for which filter, ma?
Ma'am, for this only we have shown, ma'am.
Yes, yes, I told you. That's what I remember. For this filter only, right? Exactly. Right. Soumya, very good. Okay. Draw the frequency response for the filter design. Okay. And here, just same steps we apply here. FH, you know, C2, C3 equal to some value, any value, random value you can take. Then you calculate what is R. And after that, RF equal to 0.586 times R1. And R1, any value you take, just some value, some 20K, 7 kilo. That means, what is this 27? Why not 26? Why not 28? You may feel. So here, while assuming these values, you should have some little practical knowledge. That means you should know what are the various standard values of resistors. Okay. So here I think I can ask any one of you. I told you that you refer Bell textbook, or you refer what is that? Boylsted or Bell. So many textbooks on electronic devices and components. Okay. Electronic devices and circuits, sometimes electronic components, when some books are there, you refer. Otherwise, directly in internet, you can search for standard values of resistors and capacitors. If possible, any one of you, please collect these values and share here, so that all our friends will be will feel happy. And always you remember that we know in Telugu we have one proverb, right? Anni danamula kanna vidya danam goppadi. That means if you share with others your knowledge, you will increase your knowledge, right? So when you share your knowledge with others, you will increase your knowledge. Only what is that? Only here that principle works. Of course, if you have one apple, if you share apple, instead of eating one apple, you may have to eat only half of it, because you are sharing half to others. But whereas in related to your studies, when you have some knowledge, when you share with others, it will become double. Your knowledge multiplies. Therefore, whenever you get an opportunity, you try to explain these concepts to your friends, right? I think nowadays you might be making calls to each other. So instead of, hey, have you heard about today's class? Have you listened? I did not follow, yeah. Instead of saying that, you can say, see, have you followed that class? Today's class, I liked it very much. See, have you followed that concept? What is this higher order filter, or what is this frequency scaling? So if you have followed, okay, otherwise I will explain to you. I liked that explanation, or I liked that concept. So such things you have to discuss among yourselves, right? So don't discuss negative things. Okay, try to add some value to your friends. If they followed, okay. If they are not able to follow, you explain. When you share your knowledge gets multiplied. You remember that. That is, otherwise, when I am teaching, all of you are listening at the same time, but some of you are getting 80%, some are getting 60%. What is the difference? Some are not paying attention. Okay, so whether they pay attention or not, my knowledge is increasing. Similarly, your knowledge also increases when you share your knowledge, right? So keep that in mind. Then second method, what we have done for the low pass filter, same thing you can do. That means for low pass filter design, first order filter we have designed now. Same component values you can take and you can draw the same circuit. So that is the simplest method. And today's class, we have planned to discuss about high pass first order high pass Butterworth filter, right? So when I say in today's class we are going to learn this, means unless you understand that the previous one, you cannot understand this. Therefore, when I explained all that, that means I am giving foundation to this this new filter, right? Now, without recollecting all that, simply I say, Seema, yesterday's class or day before yesterday's class, I have explained about low pass filter. It is same as low pass filter except this, and I can move this slide within a second or within a minute. But whether you recollect or not, I have recollected so that you will have clarity in your mind, and you will not forget, and you will follow very easily when I move forward from this slide. That is my idea, right? So now this filter, high pass Butterworth filter, right? So same low pass filter. Just now we have seen all these components are same. Only thing, earlier we have capacitor here and resistor there. Now R and C components are exchanged. R and C components are exchanged, and that's all. No other modification. No other modification, right? So now this is a high pass Butterworth filter. I think you might have taken this circuit when I opened this class. Many of you have joined and you have taken this circuit. Okay, so assuming that you have noted down this circuit, I'm just moving little forward, right? So this is a high pass filter, and this high pass filter, I have given you the frequency response. The frequency response curves for all types of filters together at the introductory level, right? Now here, let us see, this is the voltage or gain magnitude or voltage. Here it is, we are indicating voltage, right? It is not converted into dBs, just voltage gain we are saying. If you convert this gain into dBs, gain magnitude in dBs we say, right? Then along x-axis frequency, right? And then it is a high pass filter. That means for low frequencies, when you vary input frequency, there is attenuation. Gain is very less, like that. Okay, until you reach a particular frequency. That means one cutoff frequency, gain will be very less, right? And after that, after reaching this FL, and gain will be some 0.707 times that of the maximum gain, that is the filter passband gain. And after that, for frequencies above cutoff frequency, the gain is maximum. So therefore, we get a response like this. Okay. So this is called stop band, and this is called pass band. So this is the frequency response curve of the filter, right? High pass filter. And here also, if you take slope for this curve, you will get 20, right? So that means this here, it is always 20 dB per decade. This when you convert into dBs, it will be 20 dB per decade, and this is AF, and this is 3 dB down to that of AF, right? So this is the frequency response curve. I hope you have taken this frequency response curve when I am explaining, right? Now, just now we have mentioned what is V naught. V naught is equal to 1 plus RF by R1 into V in, right? So what is V in or V1? Let me show you here, right? So this is V1, right? V in or V1, whatever you say, right? V in or V1, whatever we want, we can say, right? Now what is this? This is what I have explained now. Similar to that, again, you have this V naught is equal to 1 plus RF by R1, 1 plus RF by R1, 1 plus RF by R1 into V, whether you want to write it as V in or V1 or whatever you want, that term you write here. So now our aim is to calculate what is V1. Earlier capacitor was here, resistor was there. Now resistor is here, capacitor is there. So therefore now we apply voltage divider rule, right? Just now we have done, once again I'm telling you. So voltage, according to voltage divider rule, this V1 is equal to V in into, okay, of course V in into always. And how do we write this? R divided by R minus JXC, right? So that means required branch impedance divided by total impedance into Vn. So we write that. So with that experience directly, and after that minus Jx is equal to 1 by 2 pi Fc. What all we have done, you just do that. And finally, that V1, what I have indicated there, we will get it as J2 pi F RC divided by 1 plus J2 pi F RC into Vin, right? So previous case, we got in a different manner, right? I think very long back. This is the circuit that we have, I mean, this is the procedure that we have followed, right? Here V1 is equal to opposite, I mean, required branch resistance by total resistance or impedance. That is what we have written, right? And again, J equal to minus square root of minus 1 minus Jx is equal to 1 by J2 pi Fc. After that, you divide numerator and denominator with minus Jxc. And finally, V1, you will be able to express like this, okay? Similar to that, for this high pass filter also, I expect you to do, and when you do all that, you will get the expression that I am showing now. That is, V0 is equal to 1 plus RF by R1 into J2 by F RC divided by 1 plus J, yes, first order high pass Butterworth filter response 1 plus J2 pi F RC into Vn. So are you able to understand how I got this equation? V0? Respond in your chat box. Are you able to understand how I have expressed V0? Where is this new message? Okay, so one of you just express whether you have followed the equation of V0 or not. Otherwise, I repeat, no problem for me. Yes or no? We teachers ask smallest questions to you. We don't want to waste your energy. Either you say yes or no. Or shall I repeat, ma'am? Shall I repeat once? Okay. Yes, someone gave. Okay, repeat. Okay. So let me show you this. Okay. Here we want to express V0. V0 is equal to the OpAmp is connected in non-inverting mode. Therefore, its V0 is equal to 1 plus RF by R1 into Vin. Vin means voltage that is applied exactly at the non-inverting input terminal. So this V1 we want to write. So what we have done in low pass filter, same way we are doing, right? V0 is equal to 1 plus Rf by R1 into V1. So what is this V1? To calculate this V1, you use voltage divider rule. Voltage divider rule. So what is this voltage divider rule? V1 is equal to V1 is equal to V1 is equal to what we write? R divided by, that means required branch resistance R divided by R minus JXC, R minus JXC into V in, into V in. What is the difficulty in mentioning this voltage divider rule? So many times, each time when I use this voltage divider rule, I am explaining. What is the difficulty here? Actually, in third year, you should have full command on this voltage divider rule, right? So, okay. Second year, what you have learned, let me leave it. But after coming to third year, in this unit itself, I have repeated several times, not one time or two times or three times. Several times I have repeated, right? Voltage divider rule. What is this voltage divider rule? The voltage across the component required is equal to that branch resistance divided by total resistance into input voltage. So when we have like this, so therefore R divided by R minus JXC into V in. Followed. Now for this, what I'm asking you to do is, what is that? Square root of, I mean J equal to square root of 1, and after that minus JXC is equal to 1 by J2 pi FC. You write all those, and after that divide numerator and denominator with the minus JXC. Just now I have calculated for a low pass filter. Similar to that, you also do it for this filter, and then you rearrange this equation, and then you will get V0 is equal to 1 plus Rf by R1. 1 plus this same 1 plus Rf by R1, and V1 is equal to what you will get? J2 pi f RC divided by 1 plus J2 pi f RC into V in you will get. Okay. So you please do this. Otherwise, it will be like what we say. Directly, if you write, if you get practice, then only you will be able to write in the examination, right? So why I have not written here? Actually, if I simply show these two equations in the slide, I need not give that much explanation, right? But why I'm struggling that much means I want you to apply your knowledge that you have gained earlier and use that knowledge here. So I'm trying for that. That's why I'm trying, and I'm training you to do that. That's why I'm asking you to do this, right? Otherwise, it is 1 minute. It is a matter of 1 minute for me. Just if I project that slide, you will just directly follow. But I want you to do on your own. So I want to give some exercise to your brain. Okay. So please do that. And V0 is equal to this much. And when you express this, right, you write what is FL. FL is equal to 1 by 2 pi RC, right? So wherever we have J, you leave it, right? F also you leave. Then 2 pi RC we have. So you write FL is equal to 1 by 2 pi RC. So here also J, F, okay, 2 pi RC. So in that place, FL equal to 1 by J, FL is equal to 1 by 2 pi RC. So gain magnitude, gain voltage gain, you will get V0 by V in is equal to AF into JF by FL divided by 1 plus J F by FL. So this is the gain magnitude equation that we get. Okay. So you know what is AF? Pass band gain, like in low pass filter. F is the input signal frequency, and FL is the low cutoff frequency. That is why we say low cutoff frequency for high pass filter. You know, we say low cutoff frequency. For low pass filter, we say high cutoff frequency, because all low frequencies are allowed to pass. As we increase frequency at certain high frequency, it starts providing attenuation. this is a low pass filter. Okay, that's why we call this frequency as high cutoff frequency. Whereas high pass filter, it provides high pass filter. Okay, let me show you here. For low frequencies, it provides more attenuation, but at certain low frequency, it starts giving from certain low frequency, it starts providing. I mean, it allows those frequency signals to pass. So, what is that particular low frequency that it is not allowing? So that cutoff frequency is called low cutoff frequency. Otherwise, we say all the low frequencies are attenuated and high frequencies are allowed to pass. So from which frequency it is allowing, so that is called low cutoff frequency, right? And then high cutoff frequency. Otherwise, yes, instead of FL and FH, even if you write FC, that is sufficient, no problem, right? Only notation that is. So low cutoff frequency. Then gain magnitude. So you please note down this problem. That is, all of you note down this problem and do this problem at home and come for next class, right? Design a high pass filter at a high cutoff frequency of 1 kilohertz with a pass band gain of 2, and B-bit plot the frequency response of the filter. Okay, and let me take your attendance. Be in the call until I take the attendance, because you are making me to repeat few things. I'm exceeding my time, right? Okay, what is this? Don't allow attendees to unmute something. Okay. Right, I have taken your attendance also, ma, and I will stop recording